Let us talk about miscellaneous examples and questions based on sequence and series for class 11th. If pth, qth, rth and sth terms of an AP are in GP, so pth term, qth term, rth term and sth term of an AP, they are in GP, okay? And we need to show that p minus q, q minus r and r minus s are also in GP. So these are three numbers or three terms that we need to show that these are in GP. So it would be enough to show that q minus r squared is equal to p minus q into r minus s. Or in other words, you can say this term divided by this term, that is second term divided by first, should be equal to third term divided by the second, because and it will be equal to some common ratio, right? This is what GP is. So we need to show this relation or this relation for them to be in GP. All right. So let us start the question. Now pth term of an AP, let us say this AP has got first term as small a and the common difference as d. So pth term of this AP will be a plus p minus 1 into d. Qth term of this AP will be a plus q minus 1 into d. Rth term will be a plus r minus 1 into d, and sth term will be a plus s minus 1 into d. Now these terms ap, aq, these terms ap, aq, ar, as, these are in GP. Okay, so these are already given that these are in GP. So how do I think about this is, if these are in GP, I can say that AQ by AP is equal to AR by AQ is equal to AS by AR, right? This second term divided by the first is equal to third divided by the second is equal to fourth divided by the third, because these are equal to some common ratio, right? I'm not denoting common ratio by small r because there is already small r is already used in this question. Okay, that is why I'm using this word common ratio. So this is equal to common ratio, hence these ratios are equal. Now if these ratios are equal, there is a property. For example, let us say 2 by 4 is equal to 1 by 2, or let me take some other number also. 3 by 6 is equal to 2 by 4 is equal to 1 by 2. So if 3 by 6 is equal to 1 by 2, then 3 minus 1 by 6 minus 2 will also be equal to these ratios, that is 2 by 4, right? So this is a property known as addendo. So I can add, if there is 1 by 2 equal to 2 by 4, which is obviously true, right? So I can say that 1 plus 2 by 2 plus 4 is also true, because that will be 3 by 6. Okay, if and why in this I have subtracted, so that is also possible, because 3 by 6 is also equal to minus 1 by minus 2. Now I can add these, right? So this is the property that I will use here. Why am I doing this? Because I want to create these terms, p minus q, q minus r, r minus s. And if you notice, if I subtract ap minus aq, I will have p minus q into d. Let me show you. If these two ratios are equal, then can I say this is also equal to aq minus ar divided by ap minus aq? Yes. And what is it equal to? AQ minus AR. So if I subtract AR from AQ, A will get cancelled, and from here this minus 1 will get cancelled. I will be left with Q minus R into D. So Q minus R into D. Similarly, you can check that in the denominator you will have P minus Q into D. How did I write it? I saw that q minus r, so by symmetry I said p minus q will be here. And you can check also, ap minus aq, this term minus this term, a will get cancelled, p minus q into d will remain in the denominator. So d will also get cancelled. So from this equality, I know that these ratios are equal to q minus r by p minus q. Okay, now I will compare these. So from these I will be able to say that r minus s by q minus r will also be equal to these. Okay, I hope you have got what I wanted to convey, but let me explain it once again and use a different color. See, I have shown you that these ratios are equal. Okay, so these ratios are equal, and these will also be equal to difference of this and this divided by this and this. So aq minus ar divided by ap minus aq, that gave me this relation q minus r by p minus q. So these ratios are also equal to q minus r by p minus q. And similarly I used these two, right, these two terms, and then these came out to be equal to r minus s by q minus r. So it is also equal to r minus s by q minus r. Why are these equal? You can, this is a property of ratios. 3 by 6 is equal to, let me take any number of, let us take a big number, 16 by 32. Okay, 3 by 6 is equal to 16 by 32 because we know these are equal, 1 by 2, right? So can I say that 16 minus 3 by 32 minus 6 will also be equal to these ratios? Let us check. This is 13, this is 26, so yes, it is also equal to these ratios. So if two ratios are equal, then their differences of their numerators divided by difference of their denominators will also give me the same ratio. This is the property that I've used here. So and aq minus ar will come out to be q minus r into d. This is something that is very, very basic. If you subtract these terms, you will see that this is happening. Now I think you know that the question has been solved. If I can show this much, then I can say that these terms p minus q, q minus r and r minus s, these are in GP, right? If you can say this, then this is true. As you can check, r minus s divided by q minus r is equal to q minus r divided by p minus q. So yes, these are in GP. So here is our next question. If A, B, C are in GP and this relation is given, then we need to prove that X, Y, Z are in AP. So let us first of all use the given information. A raised to power 1 by X equals B raised to power 1 by Y is equal to C raised to power 1 by Z. Whenever these type of equalities are given, I just assume it to be equal to some constant K. Okay. Now, because these are equal, these have to be equal to something, right? So I assume them to be equal to K. This is what I have assumed. So what can I say about A? A will be equal to K raised to power X, B will be equal to K raised to power Y, and C will be equal to K raised to power Z, right? And the other information that I have given in the question is that A, B, C are in GP. That means B squared is equal to AC. This is what is given in the question. So I will put values of B, A and C in terms of K here. So B is K raised to power Y. K raised to power Y squared is equal to K raised to power X into K raised to power Z. And here I will write 2Y is equal to this. These powers will get added up. What I mean to say is K raised to power 2Y is equal to K raised to power X plus Z. That means 2Y is equal to X plus Z. Hence I can say X, Y, Z are in AP. Because if you are able to show that 2y is equal to x plus z, I can say that these terms are in AP. Or you can also say y is equal to x plus z by 2. Okay, so these are And there is another way of saying this. You can say this y plus y is equal to x plus z, and y minus x is equal to z minus y. This is also another way of saying the same thing. So I hope you know that x, y, z are in AP. Okay, this is a good one. If A, B, C, D and P are different real numbers, these are different real numbers such that this quadratic in P is less than equals 0, then show that A, B, C, D are in GP. Alright, so this is less than 0, and if I look at this relation, this term here or this expression here, what is this expression? This is something like this. If I open it, a squared plus p squared, b squared plus p squared, c square p square. This is not plus, right? A square p square plus b square p square plus c square p square minus 2abp, 2bcp, 2cdp plus b squared plus c squared plus d squared. This is an expression that is written here, right, on the left hand side of this inequality. Why have I expanded it? Because I saw that I can convert them into complete squares, because if I club this term a square p square, abp and b square, so a square p square plus b square minus 2abp will give me ap minus b whole square, right? So I've got a term which is a whole square. Similarly, I can write other terms. For example, I can club these terms: b squared p squared and minus 2bcp and then c square, and these will become bp minus c whole square, and rest of the terms c square p square 2cdp plus d square will become cp minus d whole square. Okay, now you see this expression on the left hand side of the inequality is sum of three complete squares, and sum of squares of numbers will always be non-negative. That means it will always be greater than or equal to 0. It will always be non-negative. What does it mean? That it can minimum be 0, or it will always be, if it is not 0, then it will be greater than 0, right? So the minimum value of this expression can be 0. Hence I can say that this expression is always greater than or equal to 0, but it is given in the question that it is less than equal to 0. So I have found that it is greater than equal to 0. Now both of these statements can be true simultaneously only if the equality holds. That means for these two statements to be true simultaneously, it has to be equal to 0, right? So it is equal to 0. Why do I say that? Because you can always write that 3 is less than equal 3. This is a correct statement, because either this term written on the left hand side should be less than this or should be equal to this. If any of these relation, less than or equal to, if any of these two is satisfied, then this inequality is good, right? We have written it correctly. So if it is written that 3 is less than equal 3, it is a correct statement to say, because 3 is equal to 3. Okay, so what I mean is, if x is less than equal 3, then if x is equal to 3, it is also a solution of this inequality, right? So the only solution possible, or only situation, only scenario that is possible is that this is equal to 0. And if sum of squares of three different terms is equal to 0, then the each of these individual terms has to be equal to 0. We are talking about real numbers here, right? In real numbers, if a square plus b square plus c square is equal to 0, then a equal to b equal to c have to be 0 simultaneously, right? This is the only possible scenario, because the minimum value it can have is 0, minimum value it can have is 0, minimum value it can have is 0. So all of these should have the minimum value, that is 0, for their sum to be equal to 0. I hope you know this basic thing. So this is equal to 0 means ap minus b equal to 0. That means a p is equal to b by a, right? What I need to show is a, b, c, d are in GP. So if I can show that b by a equal to c by b equal to d by c, then I'll be able to show that a, b, c and d are in GP. Alright. So, and this b, p minus c is equal to 0. That means p will be equal to c by b, and c, p minus d is equal to 0. That means p will be equal to d by c. Now these three are equal, so because these are equal to p, so b by a is equal to c by b is equal to d by c. This is what I wanted to show, right? Because I need to show that a, b, c, d are in GP. So b by a is equal to c by b is equal to d by c. Hence I can say a, b, c, d are in GP. Alright, I hope you have understood. If PQ are in GP, then the equations. So first information is that PQ are in GP. So I can reduce that Q squared is equal to PR. Okay, and the equations this and this have a common root. Alright, so let us think about the roots of this equation first. Px squared plus 2qx plus r equals 0. Okay, how do we find the roots? First of all, we will find the discriminant. What is that? 2q squared minus 4 into p into r, which is equal to 4q squared minus 4pr, which is equal to 4q squared minus pr. Now I know that q square equal to pr, that means q square minus pr will be 0. So this is equal to 4 into 0, hence equal to 0. So the discriminant of this quadratic is 0, hence its roots will be equal, and they will be equal to minus b by 2a, that is minus 2q by 2p. So minus q by p and minus q by p. These will be the roots of this quadratic equation. And we know that these two quadratic equations have a common root. So, and this first quadratic has got two equal roots. So this is also a root of the second quadratic that is written here, dx square minus 2 plus 2ex plus f equal to 0. So if it is also a root of the second quadratic equation, then it will satisfy that equation. What do I mean is, if it is a root of dx squared plus 2ex plus f equal to 0, then if I replace x with minus q by p, it will satisfy it, 2e into minus q by p plus f is equal to 0. So this will also be true, and I can further write it as dq squared, right, and in the denominator I'll have p square. So I can take p squared as my LCM. So I'll have to multiply this term with p, so it will become minus 2 EQP, and I have to multiply f with p squared, and from the denominator p squared will vanish because p cannot be 0, as this is a quadratic equation and p is coefficient of x square, right? So p cannot be equal to 0, so p squared can be simply multiplied on the right hand side with 0, hence it will vanish. So this is the quadratic equation that I've got. Now if I divide this quadratic, by pq squared, what will happen? Why am I dividing it by pq squared? Let me show you. If I divide it by pq squared, you will have d by p minus 2e by q plus fp by pr. Why have I written pr here? Because q squared will be equal to pr. Okay, so it will be equal to 0. Hence, I can say, I'll take this term on the right hand side. So 2e by q is equal to d upon p plus f upon r. And now can you say that this number, what I mean is, if I can show that 2y is equal to x plus z, I can say that x, y, z are in AP, right? This is what I can say. Now I have shown you twice of E by Q is equal to D by P plus F by R. So can I say that D by P, E by Q and F by R are in AP? Yes, I can say that. So this is what I had to show. After this step, okay, I have divided it by PQ squared. Okay, this is a simple manipulation. You can do it in any other way that you want. And here, rather than writing q squared, I have written pr. Okay, another way to think about this can be that you convert this q square by pr here itself and then proceed. Okay, so this was the end of miscellaneous examples. After this, I think we will have miscellaneous exercise. Yes, so we will cover those questions in the next lecture. So this was about miscellaneous examples of sequence and series.